Our next speaker for this special plenary session will be Laura Cadenati from Georgia Tech, and she's going to be telling us about LIGO and Virgo and the promise of multi-messenger astrophysics. Thank you for being here, Laura.
Thank you, Deirdre. Thank you, Michael. So let me see, I'm gonna share my screen. Does this look okay? Can you all see my slides? Okay.
Looks good.
Okay, good, thank you. All right, so first of all, thank you for being here so early in the morning for some of you, especially on the West Coast. And thank you to the APS for giving me the opportunity to talk to you today about the role that gravitational waves are gonna have in this new era of multi-messenger observations. So I wanna start with a few words to introduce gravitational waves. Gravitational waves are ripples in the fabric of space-time. They are a prediction of Einstein's theory of general relativity, and they are produced by rapid changes in the shape and orientation of massive objects. So it's really a small perturbation to the G mu nu metric. As they propagate, they carry and they bring to us information from the coherent relativistic motion of large masses. So in this little animation you see here, this is a simulation, a representation of what two objects, two black holes or two neutron stars that are rotating in spiraling around each other. That's what they would do, the gravitational wave, they would produce the ripples in this two-dimensional fabric of space-time. So the gravitational waves, according to GR, propagate at the speed of light. They are transverse waves with two polarizations, plus and cross. And physically, what we would go after is a dimensionless strain, h of t, h is a function of time, which is a relative change in length, which is inversely proportional to the distance from the source, and is proportional to the acceleration of the source mass quadrupole moment. So to detect gravitational waves, we need to have astrophysical sources that are changing their shape in an asymmetric form. To detect gravitational waves, the instruments that we are using are interferometers. So to the left here, you see a sketch of how an interferometer works. So we have a laser beam that is split by a beam splitter mirror. The two beams travel along two arms that are 4 kilometers long, bounce back after hitting the test masses, the mirrors, come back, recombine, and what we're monitoring is the interference pattern as these two signals recombine. So the signal that we read is a voltage at the photodetector, this signal, the way we characterize and we quantify the sensitivity of our detector is in plots such as the one to the right. So this is a sensitivity plot where on the horizontal axis we have the frequency of the gravitational waves. So that's the frequency of the stretching and squeezing that's applied by the gravitational wave. And on the vertical axis is the strain. That's in units of 1 per square root of Hertz. That's the square root of the power spectral density. And so the white line represents the sensitivity of the LIGO detectors at design. That's design sensitivity. And the limiting factor for this sensitivity is quantum noise. So a low frequency is a radiation pressure, the pressure exerted by the photons of the laser that's in the arm cavities. And at high frequency is the shot noise. The other limiting factor is the Brownian noise, the thermal noise in the coating surfaces of the mirror of the test masses. And then we have other sources of noise, such as thermal noise in the suspension for the mirrors, seismic noise, Newtonian gravity noise, excess gas in the beam tubes. Those are noise sources that in the current designs are under control. The detectors that I mentioned and described so far are the LIGO detectors. So these are the two interferometers that are in the United States. There is one in Hanford, Washington State, and one in Livingston, Louisiana. They are separated by the equivalent of 10 milliseconds in light travel time. There is another detector that's working with us, acquiring data, analyzing, and has been doing so since 2006. That's Virgo. Virgo is a 3-kilometer baseline interferometer, and is in Italy. Part of our collaboration is also GW600. This is a shorter baseline interferometer, 600 meters. And then on this graph, you also see pointers for CAGRA. So CAGRA is an interferometer in Japan that just recently started taking science data and just recently joined the data run. That's a similar setup, but underground and aiming to use cryogenic techniques as well. And then there is a plan to build a detector in India, so that's LIGO India. And that's in the plan for the next few years. So all in all, we're talking about a network of 5 detectors at a kilometer scale baseline. And I will come back later to emphasize the importance of having a full network of detector rather than just 2. So what kind of things can we learn from gravitational waves? So gravitational waves are, we refer to them as a new messenger, one of the new messengers in multi-messenger astrophysics. And that's because they are an entirely new way to probe the universe, different from what we can learn from photons or from neutrinos and particles. There are a plethora of questions that gravitational waves can help us answer. Questions that are rooted into physics. So is general relativity the correct theory of gravity? How does matter behave under extreme gravity? What's the equation of state of neutron stars and nuclear matters? There are questions that are deeply rooted in astrophysics and astronomy. So what is powering the short gamma ray bursts that are the brightest event in the universe? How do stars explode? How many stellar mass black holes are there in the universe? Do intermediate mass black holes even exist? And then there are questions that are pertinent to cosmology and the origin of the universe. So can we detect primordial gravitational waves? What is the value of the Hubble constant? Do primordial black holes exist? So this is just a partial list of the many questions where gravitational wave can give us a new insight, because as I was saying earlier, they tell us things that happen inside the source. And so they're a complementary sense, a complementary probe to electromagnetic waves and to particles. So gravitational waves were discovered, gravitational waves were discovered in 2015. GW150914 was the first binary black hole merger that was discovered shortly after the advanced LIGO detector were turned on. So this is a very famous picture that is from the discovery paper, and shows at the very top the gravitational wave signal. So that's the data from Hanford and Livingston after just applying a bandpass filter. Then we see the numerical relativity waveforms that are a match to the data, the residual, and then in the bottom row, we see the time frequency map, the chirp. So that's a way in which we visualize these signals that are typical of the collision of 2 compact objects, a signal that increases in frequency and amplitude up until the moment of the merge. We have seen since then more such events. Sorry, my screen seems to have frozen. Oops, okay. We've seen more such events. So this is a mugshot, if you want, of the 10 gravitational wave events from the collision of binary black holes that have been discovered by LIGO and Virgo in their first 2 science runs. They're all a little bit different in terms of the frequency, the amplitudes, the wobbling, and the characteristic of the signals are what tell us about the properties of the source. At the very bottom, you see an event that's much longer in amplitude. So Typically, binary black holes, we are sensitive to the large fraction of a second of their signature. The last one is different because it's not due to the collision of binary black holes, but to the collision of two neutron stars. And so that's the event that we've all been hearing a lot. That's our second groundbreaking discovery. That's GW170817, where a gravitational wave signal that is corresponding to the property of a binary neutron star was detected within 2 seconds of a gamma ray burst. In this plot here, you see data from Fermi. And then this event was advertised to the astronomical community and followed up by a slew of observation across the full electromagnetic spectrum. So the plot to the left here is a summary of all the observations that were performed. The source was localized within 12 hours. Once the source was localized, it was followed up at all possible bands. And so that was the first time we had a multi-messenger discovery, a multi-messenger observation that involves gravitational waves. And science was done from this event. Here I'm just giving a couple of examples. From GW170917, we learned that neutron star merger are the engine for at least some types of short gamma ray bursts. We have done a first test of using gravitational waves as a standard sirens to measure the Hubble constant. So the problem here is to measure the distance of objects for which we know the redshift, and being able to establish the relationship between the distance of the object, the velocity at which they're moving away from us to the expansion of the universe. And so the gravitational wave from the binary neutron star offered us a new yardstick to measure the scale of the universe, and a complementary way to measure the Hubble constant to what's known from measurement from supernovae or cosmological measurements from Planck. And then it was possible to identify through the electromagnetic follow-up, it was possible to associate this event to a kilonova, so to our processes which we now believe are associated to the production of heavy elements that follow the merger itself. So these are just some of the examples of the many, many results that have followed GW170817 in terms of multi-messenger observations. And so the field of multi-messenger astrophysics is growing, is booming. We had a very nice session yesterday at this conference, session GO6, which gave a wonderful summary of the multi-messenger potential, bringing together results from the gravitational waves, from the electromagnetic follow-up, and then also the status of a multi-messenger observation with neutrinos. So the future was lays ahead of us is an astrophysics where photons, gravitational waves, neutrinos in joint observation are more than the sum of their parts. I mentioned the binary neutron star merger and GRB association that we got with GW170817 and GRB170817A. IceCube and Fermi at about the same time discovered an association between blazars and high energy neutrinos. So that's a TXS 0506 plus 056. And then we have another example of multi-messenger astrophysics that goes way back to 1887 with supernova 1987A, where the supernova was associated to a flux of neutrinos. And that also is something that we look forward to as a potential signature moving forwards when we're gonna have the next galactic supernova. And then what's probably the most exciting is what we don't know to expect. So the unknown that we can uncover once the multi-messenger astrophysics has achieved its full potential. And so what are the ingredients that we want to pursue to achieve, exploit the full potential of multi-messenger astrophysics? So I'm focusing here on gravitational waves because that's what I do. Sorry, got something appearing on my screen that I don't seem to be able to get rid of. Sorry. Resume sharing. Okay, I'm sorry. I had a window popping up on my screen that I was not expecting. This is part of what happens in this unusual way of presenting. Okay, so from the gravitational wave side, what we need to build, what we've been focusing on, are three ingredients. One, we need to work on the event rate. So that means improving our detectors, having detectors with higher sensitivity, so that we can probe deeper into the universe and increase the number of events that we are sensitive to and we can share to the astronomical community. We need to improve the localization. So this is where having a network of detectors helps us, because the more detector we have, the better triangulation we can do, the better localization of our sources. And that's what enables follow-up. We need rapid alerts, and that's something we're working towards, reducing more and more the time between detecting an event in the gravitational wave data and sending it out and alerting the community so that an electromagnetic follow-up can follow. And then, of course, we need to have simultaneous coordination with the electromagnetic and particle observatory. And so the way to the future is to have a simultaneous observation of objects such as binary neutron star mergers, where we can simultaneously detect the signal from gravitational waves, from the optical, from radio, from X-ray, and from possible fluxes of high energy neutrinos. So that's the future that we need to strive towards. So I'm going to spend a little bit time now talking about the present, the upcoming future, and the longer term future. So where are we now? So this is a plot from the observing scenario document that LIGO, Virgo, and CAGRA have been working towards. Now this plan is preceding the early suspension of the third science round. So I'll say more about that in a minute. So what you see here is, as a function of time over the years, what is the sensitivity of the detectors and run coordination between LIGO, Virgo, and CAGRA. The metric that we're using is the range for binary neutron stars. So what's the average distance at which we can see or sense the merger of two neutron stars? And so there was 80 megaparsec in the first science run back in 2015, 100 megaparsec in the second science run, so that was 2017. And now we just concluded the third science run at a sensitivity between 110 and 130 megaparsec for binary neutron stars. And then Virgo has been joining us in O2 and has been running with us during O3. And as I was mentioning, CAGRA started acquiring data towards the end of the O3 run, although at a lower sensitivity than was prospected here. Now, the O3 run, which is what I'm going to be focusing on now, this has been, was supposed to last a full year. In reality, it was interrupted on March 27, 2020, and that's in response to the COVID-19 pandemic, which has affected LIGO Virgo as the rest of the world. So the observing run 03 ended 1 month before the 12-month run. And that was in order to shut down the observatory sites for the safety of the public, the staff, and the scientists. Now, despite losing the last month of data acquisition, the run was a success, and the data is being analyzed. We have lots of results in preparation. These results have been delayed as well. But there was a very interesting session on Saturday by Chadana, Maya Fishbeck, Max Easy, who presented the status and the results for the run. So hopefully you can watch that if you have not been able to see them live. So during this run, the sensitivity of Virgo and Hanford and LIGO Observatory was improved with respect to the O2 run. So what you see here are histograms of the range in small chunks of time throughout the first half of the run. And we have a duty cycle with 3 detectors running for 44% of the time. 37% of the time with at least 2, and 15% of the time there was a single observatory. The main improvement, the main innovation in O3 when it comes to multi-messenger astrophysics is that we set up a rapid alert system so that whenever an event was identified in the live data, a trigger was distributed through the GCN infrastructure to enable follow-ups. And so what you see here is as a function of time, when there is a little icon on each day when there was an alert. And so you can get a sense of the frequency of these events. These are the louder events that were identified online, and they had a preliminary online classification into black hole, or we marked when there was likely a neutron star or neutron star black hole. So as you see, it has been a very exciting run with 56 event candidates that have been sent out for follow-up. And to this date, we've published results for 2 of these events. But before I go there, just because we're talking about multi-messenger, I wanted to show you an example of the information that was shared for these events. So for each of these events, we shared a preliminary classification, a rough identification of the distance. So those are those histograms over there. And then a sky map. And so the sky map is important because it's what enabled the follow-up. And so in the first of this event, the sky map, the error region is pretty small. So I put a little red circle over there. It's 50 square degrees, and that's because we had 3 detectors that detected these events. In the second case, the event was only seen by Hanford and Livingston. So with 2 detectors, we can at best identify on a great circle. So this is kind of this very spread error region. It was a 1375 square degree error region. And then in cases where we only had one of the LIGO detectors and Virgo, the error region was even larger, order of now 10,000 square degrees. And that's because of the different alignments of the detectors. So talking about LIGO Virgo detection, I want to mention the 2 events that we'll be publishing about. So the first one is GW150419. So this was a compact binary coalescence with total mass 3.4 solar masses. So this is likely a binary neutron star detection. The error region was pretty wide, and that's because we could only use data from Livingston and Virgo. The first alert actually only came from LIGO Livingston data. Virgo was only used to build the sky map. And then the interesting feature about this event is that it's an outlier of the observed galactic binary neutron star system masses. So this raises interesting question on the origin of this binary neutron star. The second event that I wanted to mention in brief here is a GW150412. This was announced at this conference on Saturday, during Saturday session. And now what's interesting about this event is the first time we have 2 very different masses. So this is a simulation that's kind of stopped here on me. Let's see. This is a simulation of, from numerical relativity of the merger of an 8 solar mass and a 30 solar mass black holes. I'm sorry, the simulation here, the video froze. I wanted to show you the last few seconds. Let's see if it goes now, okay? And so this is interesting because it's the first instance of unequal masses. So interesting question on the formation scenario for these events. And also it's the first time we got evidence of higher harmonics in the data. So typically the gravitational wave frequency for the merger of two black holes, it's at the level of twice the frequency of rotation for the two objects. In this event, we got hints of the presence of a higher harmonic. And that's what we would expect according to general relativity when we have the wobbling induced by having a small mass and a high mass rotating around each other. And so studies of this, this is again, seeing more of this will enable us to understand a little bit better what's the possible origin of this event. Now, let me move towards the near future. So the near future, by near future, I mean the next decades. Here is again that chart I showed you earlier, those observing scenarios. Now, this plan could be affected by the pandemic, and that's because the ability of perform the upgrades that are going to be needed to have 04 and 05 at the prospective sensitivity will require travel, face-to-face contact, so we may have delays in this. But as of 2 months ago, the plan was to have an 04 run starting in January 2022. And the plan for that is to achieve a full sensitivity for the LIGO and the Virgo detectors. So complete the commissioning that would get us to under 60 to 190 megaparsec for binary neutron stars in LIGO, 90 to 120 in Virgo. And the target for Calgary is to achieve the order of between 50 and 130 megaparsec. So that's the plan for 04, 1 year run at full sensitivity. And then next is what's labeled here as 05. So that's going to be in the second half of the upcoming decades. And I'm going to say something more about that next. Okay, so for 04, so this is the run where the detectors would be at design sensitivity. So what you see here are the evolution of the sensitivities and noise curves for LIGO and for Virgo, and the target for 04 and the target for 05. So you see how the fact that the noise curve is lower reflects into a bigger reach, so a bigger volume range. And here we go. And the expectation is for 04 to have hundreds of binary black hole coalescences, so order of 10 to the 2 binary black holes per year. A few neutron star black hole per year, 20 to 30 binary neutron star per year. So that's what we can expect to have. So an evolution of what we've been having so far in 03. In terms of localization, well, with going from 03 to 04, especially if we're going to be able to have Kager as a Ford detector in our run, that's going to improve the ability to localize the sources. And so this is a cumulative fraction of events where on the vertical axis is the fraction of events that are going to have an error region smaller than what's on the horizontal axis. And so both sensitivity improvement, the sensitivity improvements is going to allow us to probe deeper, and the presence of Kager in our network is going to reduce the error region. So we're talking about, just for comparison, you see the localization that was for 170817. That could be achievable for about 30% of 25-30% of our events in an 04 with 4 detectors. 05 is the era of advanced LIGO Plus and advanced Virgo Plus. So the plan here is to perform some modest upgrades to advanced LIGO and advanced Virgo, implementing technology that's already under advanced development. So for LIGO, introducing frequency-dependent squeezing, lower the coating thermal noise. And for Virgo Plus, increase the laser power, implement signal recycling, again, frequency-dependent squeezing, suppression of Newtonian noise. So overall, the goal is to improve the reach by a factor of 3, respect to 3. So that's when we're talking about hundreds to 1,000 black holes per year, order of 10 neutron star black hole per year, 2 to 300 neutron star per year. So of course, these numbers have large errors, but just look at the order of magnitude and how that is growing. Even farther into the future, now we're talking about the 2030s. There is, I'm not going to say much about this, but there is a long-term, a concept under study that's called Voyager to improve the performance in current facilities, so in the current 4-kilometer detectors, by changing the type of mirror, so going from glass to silicon, from 40 kilograms to 200 kilograms, changing the laser, possibly implementing cryogenic techniques to address the issue of thermal noise. And overall, these upgrades are aimed at a factor of 10 increase over the O2 sensitivity at the level that will give us order of 10 to the 4 binary coalescences per year. And then the path, even looking even farther, the plan, the thought is to build new facilities. So this is where Cosmic Explorer and Einstein Telescope come into play. So the goal here is to build a new detector, longer baseline. The Cosmic Explorer is an NSF-funded US conceptual design study that's well underway. The idea is to have a 40-kilometer surface observatory baseline. And the idea is that the signal grows with the length of the detector, but not most noise sources. So, the signal to noise ratio is gonna be in favor of detection and increase the sensitivity. So there is a stage 1 targeted at around 2035, which is gonna be an extension of the A+ technology, but in this longer baseline. And then stage 2, looking even farther down the road, 2045, implementation of cryogenic new material for test masses and coating. The European design, conceptual design study is called Einstein Telescope. Now this is also longer baseline detector, 10-kilometer arm length. But the idea is to go underground to mitigate the effect of seismic and Newtonian backgrounds, and also have a triangular layout, which allows for multiple detector in the same instrument. And this is going to enable measures of it's going to enable to detangle the polarization of the gravitational waves. And the detector will be in a xylophone configuration, meaning at each side, at each corner, there's going to be a low frequency detector and a high frequency detector running in parallel. The reach for this detector is going to be tremendous. So here on the right, you see the evolution as a function of time of the sensitivity of the LIGO detectors moving towards Cosmic Explorer. So that's on the left, sorry. And on the right, you see a graphical representation of what that means in terms of reaching out into the universe. And so for the Cosmic Explorer anti-telescope era, we are talking about reaching out to redshift higher than 5, so most of the expected binary black hole, and neutron stars all the way out to redshift of 5. So that's going to give us a tremendous number of signal that can be followed up and plugged into multi-messenger observations. And so the future for MMA is a future where the sensitivity of redshift reaches out to the first star and even farther. This plot here on the left is a result of simulations. Simulations that show as a function of mass what's the reachable redshift for advanced LIGO compared to Einstein Telescope, Voyager, and Cosmic Explorer. And of that table to the right, I just want you to look at the last couple of lines. So with advanced detector technology, the second generation detector that we have now, By adding Kagra and India, we can reach to a number of events of the order of 50 with a high accurate localization. But in this third generation era, we're talking about hundreds of thousands of events with very accurate localization. And so that will enable addressing questions on the formation and evolution of compact binaries, heavy element nucleosynthesis, jet physics, cosmology, and multiband gravitational wave astronomy. Because when we talk about gravitational wave, I've only been talking about LIGO, Virgo, and the potential that can be reached with the ground-based detectors. But looking even farther, there are other frequencies. There is LISA into space, pulsar timing arrays, measurements of CMB polarization that are really going to give us a broad spectrum view of the gravitational wave universe, and that will be one of the main components of multi-messenger astrophysics going onwards. That's all I have. I will end at this slide. Thank you.
Thank you. Thank you very much. It's weird not to have the applause afterwards. I should have a canned applause. That would be fun. Thank you very much, Laura, for that talk. We have time for a couple questions, which I have seen in the chat window. Victor Mocab asks if the whether or how the impact of the strong gravity on the amplitudes of standard model processes is taken into account in the description of the neutron stars or black hole mergers.
Oh, that's a great question. I think at this point, all the modeling I've seen is still in a standard model realm, but I know that there are several studies and exploration of what can be said outside the standard model. So probing into the role of exotic matter into the neutron stars and how that's affecting the equation of states. That's all we can say is going after the effects of this into the wave. Once this is represented in waveforms, that we can actually look at the impacts on the waveform itself near the merger or in the post-merger stage. So that's an whole area that is still under development and would be fertile ground for third generation observations.